In Module 10, Section 2, we will discuss multiplying and dividing rational expressions. When multiplying rational expressions, we simply need to multiply the numerators together and then multiply the denominators together. However, when we do this, our result may not be in simplified form, so it's easier to use the following technique. To multiply rational expressions, the first step is to completely factor all numerators and denominators. Then we will multiply numerators and multiply denominators, and finally simplify or write the product in lowest terms by dividing out common factors. Let's try an example. 6x squared divided by 10x cubed times 5x over 12. Let's start by finding the prime factorization of each numerator and denominator. Remember, you can find the prime factorization by writing a factor tree for that number. The prime factorization of 6 is 2 times 3. X squared is x times x over. The prime factorization of 10 is 2 times 5. X cubed means we have 3 factors of x. Times the second fraction, 5 is prime, so we write 5 times x over 12 becomes 2 times 2 times 3. And when we're multiplying, we can just connect our fractions, put a multiplication symbol between each numerator and each denominator, and then cancel any like factors from the numerator and denominator. So starting with the 2's in the numerator and denominator, we then have a factor of 3. And we see there is also a factor of 3 in the denominator. We have 1, 2, 3 factors of x that will cancel. We then come to a factor of 5 in the numerator. There's also a factor of 5 in the denominator. And we've canceled the entire numerator. So we put a placeholder of 1. In the denominator, we have 2 times 2, which is 4. Example. Here we have m minus n squared over m plus n times m over m squared minus mn. Remember, our first step is to factor completely. We can rewrite m minus n squared as m minus n times m minus n over m plus n, nothing factors here, times m. Again, we can't factor anything out of m. However, in its denominator, m squared minus mn, those two terms have a common factor of m. So we factor in m, and we are left with m minus n. Now, just like in the last example, we connect our fractions because we're multiplying. Just write a multiplication symbol in between each numerator and each denominator. Now let's cancel like factors. We have an m minus n in common on top and bottom. We also have a factor of m in common on top and bottom. M minus n and m plus n are not common factors. They're not the same. So on top, we are left with an m minus n, and the denominator, m plus n. Rational expressions, just like when we were dividing fractions, we first change our operation from division to multiplication and flip our second fraction. Then we will work the problem just like we did the last few examples. Divide by a rational expression, we must multiply by its reciprocal. So let's try that. We want to divide x plus 3 squared over 5 divided by 5x plus 15 over 25. So the first step is to simply rewrite this as a multiplication problem. X plus 3 to the second power over 5 times the reciprocal of the second fraction, 25 over 5x plus 15. Now at this point, we begin to factor and cross out like factors. X plus 3 squared is x plus 3 times x plus 3. 5 is prime, so it doesn't factor, times 25 can be rewritten as 5 times 5 over 5x plus 15 has a greatest common factor of 5, so that becomes 5 times x plus 3. Just like in the last examples, we just make this one fraction with multiplication signs in between each numerator and denominator, and we start canceling. So we have a factor of x plus 3 in common that cancels out. We also have 2 factors of 5 that cancel out. Left with x plus 3, no denominator, so this isn't a fraction anymore. Example, x plus 3 squared over x minus 3 divided by x squared minus 9 over 3x minus 9. Again, our first step is to rewrite this as a multiplication problem. To do so, we change the operation from division to multiplication, and we flip the second fraction. Once we do this, We now factor each numerator and each denominator. X plus 3 squared, just like in the last example, is x plus 3 times x plus 3. X minus 3 doesn't factor at all. Times, the next numerator has a GCF of 3, so we factor out 3, left with 3 times x minus 3. And in the denominator, x squared minus 9. Let's do this off to the side. Hopefully you remember this from the last module. X squared minus 9 is the same thing as x squared minus 3 squared. And anytime we could rewrite something in the form of a number squared minus a number squared, then this was a difference of squares. We wrote the first term twice, the second term twice, added in the first parentheses, and subtracted in the second. So x plus 3 times x minus 3. We connect the fractions, make sure we're multiplying between each term for each factor on top and bottom, and we start canceling. So we have a factor of x plus 3 on top and bottom that cancels. We have a factor of x minus 3 on top and bottom that cancels, and that's it. So on top we're left with an x plus 3 times 3, and I'm going to rewrite this with the smallest factors first. So I'll write 3 times x plus 3 over, in the denominator we just have x minus 3. X squared minus 4 all over 20x divided by 2 minus x over 5xy. Again, the first thing we do is rewrite this as a multiplication problem. So x squared minus 4 over 20x times the reciprocal 5xy over 2 minus x. At this point, we want to factor. 4, we could write 4 as 2 squared, so this is a difference of squares factorization, x plus 2, x minus 2. The prime factorization of 20 is 2 times 2 times 5. That would be times x because it's 20x. Times 5xy is just 5 times x times y. All over 2 minus x. Now remember, in the last section, we had a trick. If we wanted 2 minus x to look like x minus 2, they only differed by a negative sign, so we could factor out a negative 1 and reverse the order of our subtraction. We're going to do that here. Negative 1 times x minus 2. At this point, we connect the fractions, make sure we're multiplying between each numerator and denominator, and let's cancel common factors. So in the numerator, the first factor we come across that has a common factor in the denominator is x minus 2. We then have a common factor of 5 and a common factor of x. At this point, let's multiply the factors that are left in the numerator and denominator. We have x plus 2 times y. I like to write the smaller factors first, so y times x plus 2 over. In the denominator, we have 2 times negative 1, which is negative 4. I don't like to write my negative sign in the denominator. It's perfectly fine. So I would write it either with the numerator or just in front of the fraction. We want to divide 5 plus x over 6, and that is being divided by a second fraction, 5 plus x over 7. Let's just rewrite it with a division symbol so it doesn't look as confusing. 5 plus x over 6 divided by 5 plus x over 7. Once we have a division problem, and we had a division problem to begin with, we just wrote it in a different form. We first change it to a multiplication problem. We do that by changing the operation to multiplication and flipping our second fraction. We then factor each numerator and denominator, and we can look at each numerator and denominator and see that nothing is factorable here. So let's go ahead and connect our fractions, multiply the factors in each numerator and denominator, and then cancel like factors. Here we have a 5 plus x on top and bottom that will cancel, and we are left with 7 over 6. We want to talk about different units of measure and being able to convert between different units of measure. One method is to use unit fractions that are equivalent to 1, but with different measurements in the numerator and the denominator. To do this, we will multiply the unit fractions like rational expressions, canceling common units in the numerators and denominators. Here are a few useful conversions as you go through these problems. These should be some of the only ones you see. If you have any other trouble with conversions, make sure you ask your instructor. So let's try the first method that was explained for us 2 slides ago. 35 miles per hour equals x, or some unknown number of feet per second. Now this word per here is going to indicate that we are dividing. This is really 35 miles per or over 1 hour. And we are trying to eliminate the units miles and the units of hours, and in place have feet and seconds. So to do so, we're going to set up those unit fractions that were discussed 2 slides ago, and we're going to multiply numerator and denominator by the appropriate values. So if we want miles to cancel, since miles show up in the numerator, we would cancel by having miles in the denominator. Well, we're going to use the conversion that was mentioned on the last slide that took miles and replaced it with feet. And we saw that 1 mile equaled 5,280 feet. And at the same time, we want to eliminate hours and replace it with seconds. So because our unit of hours shows up in the denominator, we want to rewrite a new fraction that has hours in the numerator so that the hours will cancel. We had a conversion on the last slide that took hours and seconds and related those. And we know that in 1 hour, there are 3,600 seconds. Now at this point, because we were multiplying all of these fractions, we can just connect every fraction and put multiplication symbols between each factor, the numerator and denominator. And at this point, cancel common units. As we look, we have miles in the numerator, miles in the denominator. We have hours in the numerator, hours in the denominator. And we see that the only units left are feet over seconds, or feet per second. That's exactly what we want. So at this point, we're going to multiply all 3 numbers on top and all 3 numbers on bottom. And once we do that and divide, that will give us the number 51.33. So this becomes 51.33, and that 3 goes forever, feet per second. And we can go ahead and round this. So we would round this to, say, 51.3 feet per second. Way we can solve unit conversion problems. And this way, the method 2 might be more straightforward for some of the problems outside of the miles per hour problem. So let's say we have 1,008 square inches, and we want to know how many square feet that would be equivalent to. What we might start with is the equivalence of just inches to feet. So using the information given a few slides back, we know that there are 12 inches in 1 foot. Now, while this is a good starting point, you can see pretty quickly from the initial problem statement, we don't want inches and feet, we want square inches and square feet. So to get from inches to square inches, we would need to introduce an exponent of 2, or square both sides. When we do so, we square the unit and the number. 12 squared is 144. So this will become 144 square inches, and I'll just write it as inches squared. That means square inches equals, on the other side, 1 squared is 1, so 1 square foot, or I'll just write foot squared. Now we see we're closer. We now have square inches on the left side, square feet on the right side, but the numbers don't match. I have 144 where we would like 1,008. So we need to figure out what number we can multiply 144 by to get 1,008. And one way we can quickly do that is just divide 1,008 divided by 144. We find that that would give us 7. So if we multiply both sides of this equation by 7, that will give us 1,008 square inches equals 1 times 7 is 7, so that equals 7 square feet. So in place of the blank at the beginning of the problem, we would have 7. 1,008 square inches equals 7 square feet. It doesn't matter which method you use, or maybe some combination of the 2 methods, as long as at the end we can follow your steps and you have the correct answer.